Now that we have a little bit of a foundational understanding about matrices, we need to sort of take a side step. It's not really a step back, but it's sort of a step to the side, and we need to talk about vectors. And vectors are a closely related concept to matrices because we can always express a vector as a matrix, or we can write a vector in matrix form. And so they're really related. The important thing to know about vectors is that every vector contains two pieces of information. The first is the direction of the vector, so the direction in which the vector points. And then the second thing is the magnitude, and magnitude is just a fancy way of saying length. It really just means the length of the vector. And we always sketch a vector like a little arrow. So let's say, for instance, that I want to sketch a vector. We'll call it the vector A, and it's a vector called 3, 4. Well, this just means that if we wanted to sketch the vector A in standard position, and we'll look at other ways to sketch this in a second, but if we sketch it in standard position, that means we start at the origin and we move out toward the positive direction of the x-axis 3 units, and then up toward the positive direction of the y-axis 4 units. So that would be about there. And then we sketch in a little arrow to indicate the direction in which the vector points, and this is the vector 3, 4. Now we said this was standard position because the vector begins at the origin 0, 0, but the vector could actually start anywhere. So for instance, if we take the same vector and we maybe move it over here, or we take the same vector and we move it, let's say here, all three of these are the same vector. They're all the vector 3, 4 because they point in this 3, 4 direction. In other words, the initial point, which is the point where the vector starts, so this would be the initial point here, the initial point, and the initial point right there. The initial point doesn't matter, and neither does the terminal point. So the terminal point is the point where the vector stops. So right here, and right here, those are terminal points. The initial point and the terminal point is irrelevant. All that matters is the direction, and you can see that all of these vectors point in the same direction, and the magnitude or length. You can see that they all have the same length, which means that the vector 3, 4 describes each of these vectors. And of course, we're not limited to two-dimensional space or the two-dimensional plane. I could sketch a vector in 3-dimensional space, 4-dimensional space, 5-dimensional space, or any n-dimensional space, and it still just has the same direction and the same length. That's all that matters when you're talking about a vector. It's also important to say that we can write the vector in different ways. So this is a typical way to write a vector. We write it as almost like a coordinate point, 3, 4. And of course, if I'm sketching in standard position, the vector will point to the coordinate point 3, 4. But I can also write this vector as what we call a column vector, and it looks like a column matrix. So I have a matrix that's one column, and I write this as 3, 4. This is called a column matrix or a column vector, and it's really just a vector written in matrix form. I can also write this as a row vector or a row matrix, where I write the vector components in a row inside a matrix, and I put the 3, 4 next to each other. These are all valid ways of writing the same thing, and the reason that we talk about vectors as row matrices or column matrices is because we can actually start to see larger matrices as just a set of column vectors or a set of row vectors. So let's say, for instance, that I have a matrix, we'll call it the matrix K, and it's maybe a 2 by 4. So let's say we have 1, 0, 0, 3, and a -2, 1, 1, 4. So this is our matrix K, and what we want to recognize about matrix K is that it has a set of column vectors. Its column vectors are the individual columns of the matrix. So we could write these as, we'll call the first column vector K1, and that's going to be the column vector 1, -2. We have K2 as the column vector 0, 1. K3 is another column vector 0, 1. And K4 is the last column vector, and that's the vector 3, 4. K also has row vectors, which are just the rows of k. So we could write these row vectors in the context of row here. We'll say k1 is going to be equal to the first row, 1, 0, 0, 3, and k2, the second row, is the -2, 1, 1, 4. It's also important to understand when we look at these column vectors or the row vectors individually, the space in which they're contained. So these column vectors, they each have two components, and that tells us that each of the column vectors sits in R2. We'll go ahead and write that over here. They sit in two-dimensional space, or the two-dimensional plane, R2, which makes sense because if we were going to sketch them, if you were given a vector 1, -2, you would of course sketch it in R2 here, two-dimensional space. You wouldn't take this over into three-dimensional space and try to sketch it. You don't have the three components that you need to know the direction in which the vector would point in three-dimensional space. So because we have two components in the vector, it's going to sit in R2. So all four of these column vectors sit in R2. That's the first thing that we want to understand. The second thing that we want to understand is that because there are four vectors, we could use those four vectors to form a plane in R2, and we'll talk more about that in later lessons. If we're looking at the row vectors, we see that each of the row vectors has four components, which means each of these vectors, each of these row vectors, is going to sit in R4. We can't sketch a vector 1, 0, 0, 3 in R2. It has too many components. Because we've got four components, it sits in R4. And then because we have two row vectors, we'll be able to use them to form a two-dimensional plane that's sitting inside of R4. And again, we'll talk a lot more about these spaces R2, R3, R4, and the lines or planes or spaces that we can form within them with these vectors in later lessons. But I just wanted to make the point that when we pull out column vectors and row vectors, we have to be aware of the fact that they have different numbers of components. These column vectors have two components, these row vectors have four components, and that's going to matter as we work with these more and more. So just to make sure we understand how to sketch these vectors, let's go ahead and sketch each of these column vectors in the R2 graph that we have here. So if we sketch the vector 1, -2, let's do it in standard position. That means we're going to start at the origin and we're going to move out +1 toward the positive direction of the x-axis, and then -2 down toward the negative direction of the y-axis. We'll add arrows here in a second. And then K2 starts at the origin. We don't move in the x direction, left or right, but we'll move up 1 toward the positive direction of the y-axis. So that's going to go right there. K3 is the same as K2, so we already know what that looks like. And then K4 is the vector we already sketched here, 3, 4. So it starts at the origin and it moves out toward this point here. So if we go ahead and add tips to those, here's what those three look like. And of course, if we wanted to, let's say we wanted to take 1, -2 and sketch it in other spots, we could just translate that vector anywhere that we want to put it, and it's still the same vector. So it's still the same vector here, and it's still the same vector right here. No matter where we place that, it's still this K1 vector, 1, -2, in the same way that this 3, 4 vector was still the same when we moved it out here or when we moved it down here.